Plasma machine electronics can be a difficult control concept to understand, which can cause difficulty in how to connect all of the components together. I have a set of electronics that I am putting together for a customer. This set of electronics is the perfect project to show because it is a complete overhaul. I am using the customer's existing enclosure that came with his plasma machine, and I'm going to remove the old plasma electronics and replace it with a new, more modern controller and THC, torch-height controller, that can work with a USB or Ethernet connection. The torch-height controller also uses fiber optic cable between the main controller and the plasma machine because plasma machines can give off a lot of EMI, electromagnetic interference. All of the components that I use in this video can be found on the buildyourcnc.com website. I'm also using some tools that I don't sell on the website, but I have a link of a curated list of the tools that I use in the description. If you need your electronics to be repaired or retrofitted, I offer this service at buildyourcnc.com. Since I'm only working on the electronics, the customer will need to make sure that the plasma machine and structure is isolated from the control electronics. In most cases, this requires the plasma machine to have its own grounding rod to earth, which is also tied back to the main ground of the facility or the house where the plasma machine is located. This allows the plasma interference and stray voltage to find the quickest path to its own ground, and the control electronics is, for the most part, isolated. The best documentation that I've found for this is from the folks at Hypertherm. If you're putting your own plasma electronics together with a plasma machine, you should go to their website and take a look at that documentation. It is also recommended to get a professional electrician that is either familiar with plasma machines or has looked at proper plasma grounding documentation. With this project, I spoke to the electrician hired by the customer and decided to go the route of installing a new ground rod directly tied to the plasma machine, which is also tied back to the main ground. The reason the two grounds are tied together is to eliminate the risk of having a different voltage potential between the two grounds. If one ground has a different voltage potential of the other ground, there is a risk that the voltage difference can cause injury if they are both handled at the same time. For instance, if the plasma machine is touched, which is tied to its own ground, and the plasma electronics is touched at the same time, the difference in voltage between the two grounds will travel through the body. If the two grounds are connected, the risk is reduced, as the path of least resistance will be the connection between the two grounds. But definitely don't take my word for it, because I'm not a professional electrician. My forte is control electronics and microcontroller electronics. So definitely seek a professional electrician to sort out all of the grounding requirements of a plasma machine. I'm removing all of the electronics in the box because unfortunately none of the electronics will work with my controller. The controller that I'm using is the Pokies 57 CNC, which can be adapted to almost any type of CNC machine and robotics. It has the ability to control 8 axes and has a wealth of features including inputs, outputs, ADC, encoder inputs, standard and solid-state relays, and so much more. You may think, well, why is he removing the motor drivers? These drivers, in the existing case, are servo drives that don't use step and direction signals to move. The controller that I'm using requires either servo motors or stepper motors that use step and direction signals. Most industrial servos can be controlled with step and direction signals, but unfortunately not these. The existing controller that was used in this existing electronics had a PIC-IO V1 chip installed. This is, I'm assuming, a microchip component, and I'm guessing this enabled a general purpose input-output feature, which communicated to all of the drivers. And there are 2 other control boards that served as connection to the computer, both having 3 options of connection: Ethernet with an RJ45 connection, USB with a large Type B USB connection with an accompanying FTDI, FT232 USB serial converter chip, and a DB9, which probably serves as a standard RS232 serial connection. I can determine this because there's a MAX 232 chip right next to this connector. I'm not sure why 2 of these connection serial boards were needed in this box. If you know, leave a comment. There are some components I will be reusing. These two terminal strips will come in handy for the new connections to the torch height controller and a convenient mains power connector. The gauge of wire used to connect the power supplies to the mains power was 18 gauge with a grounding conductor. This was fine since there was only one power supply that was used for the motor power, and the max current output was only 3.6 amps DC. When converted back to the AC input using the power formula, the current is only a fraction of this at the input. I'll be using 3 power supplies, one for each stepper motor and driver, so I'll be using 2 mains cables with 16 gauge conductors. The ground, the green conductor from the mains, was tied to the chassis with a screw. I believe this is unnecessary because the chassis of each power supply is grounded, and there are screws mounting these power supplies to the uncoated bare metal of the main chassis. After I install my power supplies and resolve the ground shields when I put my components in the enclosure, I test the continuity of this with a multimeter to confirm that the shielding will be able to dissipate any EMI and send it to ground. Let me know your thoughts about this in the comments. How to organize or place components in the enclosure is probably the most difficult task when installing new electronics. Some thoughts that go through my mind are: 1. Where the motor connectors will be placed on the outside of the enclosure, which dictates where the drivers will be located. 2. Where is the most convenient place for the mains cables and how they are laid out to connect to the power supplies. 3. How I can best separate the motor coil voltage wires from the delicate signal wires. 4. Where to place the controller so that there is a convenient place to connect the computer cable to the controller. And 5. Making sure there is enough space between all of the components so I can add terminal strips and anything I forgot to add. I do go back and forth in this project where I need to place the electronics back into the main case to make sure I get things right and to add more connectors. I do this for testing as well. This is actually one of the main reasons for putting this video out there. I use these videos as a reference, so I don't need to do so much back and forth next time. When making new holes and drilling the plate that seats the electronic components, I try to do all of the drilling in the beginning so the steel chips from the drilling process doesn't enter the electronic components and potentially short something on the circuit board. Unfortunately, I do still need to go back and drill later with all of the components installed due to me missing some terminal strips, and it would be way too time consuming to disassemble the components at that point of the build. I can only try to take great care when doing this. The way to prepare exposed wire ends and secure them into terminal blocks seems to be a bone of contention. Early when I developed the pick-and-place machine and showing the videos on the build process in 2011, 11 years ago, I would tin the ends of the wires, and I got comments that the springiness was removed, causing a potential issue in the future. So I stopped doing that since it made a lot of sense. But I see this done time and time again with professionals. A few years back, I started using wire ferrules, resulting from a comment berating me for not using wire ferrules. In a video I made last year, I was berated for using wire ferrules in the comments. Each time I get comments like this, I will do extensive research and what the code requires, the National Electrical Code. From my research, I found that ferrules are not required, but they're also not ruled out as an option. Ferrules are a great way to terminate wires, and it creates a clear look and makes sure the stray strands don't wander. But due to not knowing the abilities of the person affixing the ferrules to the wire ends, they may be too loose because of the wrong size ferrule was used for the wire gauge, or the wrong tool may be used to crimp them. The burden is actually on the manufacturer of the terminal to create screw and screwless types of terminal blocks that expose conductor ends and that can be connected directly without any pre-treatment. You'll see that I don't use wire ferrules in the wiring of these electronics, but I do use them strategically in a portion of it. You'll notice that I have a bit of exposed wire coming out of the terminals on the drivers. This was more than my liking, so I trimmed them off camera. This Knipex wrench is one of my favorite tools. I know I've mentioned this in other videos, but I can't get enough of this tool. It is the most useful tool that I own. Other than trying to steer you towards my curated list where I receive affiliate fees, this list does contain the tools that I purchased myself and use on a daily basis. I'm trying something a little different here to connect the controller motor signals to the drivers. The controller uses these ribbon cables and IDC connectors for most of the connections on that controller. This creates a bit of an issue connecting the ribbon cable to the screw terminals on the drivers. I decided to create a perf board that contains a header for the ribbon cable connector and a header to insert into the screw terminals. The screw terminals have the same spacing of every other perforation on the board, which is 0.2 inches. Each perforation is 0.1 inches or 2.54 millimeters. This is the standard for most through-hole headers and electronic components. I am diagramming the connections so that the signal wires go to the correct screw terminal locations. I'll then take the perf board, insert both headers, and solder on all of the connections that's required between the two headers. It would have been easy enough to create a home-based PCB or had a PCB house do this for me, but I believe this is an adequate solution. The customer doesn't need to wait for a longer process, and there isn't any surrounding possibilities where shorts can happen. I will probably make these PCBs for future use, as this is a controller I use quite a lot. To create a mechanical connection to make the solder connection more secure and try to make the connection as thin as possible, I spread out the strands at the ends of the conductor, merge them together, and then twist them all together. I am using shielded cable for the motor cable to capture any coil EMF and take it to the earth ground. I'm using my favorite motor connectors, but there are only 4 pins for this connector. So I'm taking the shield conductor outside of the motor connector so it can be screwed to the steel enclosure that serves as the convenient connection to the earth ground. I need to make holes in the enclosure for the motor connectors. To determine the location, I am placing the electronics into the enclosure so I can locate the motor connections of the drivers and where they land at what part of the enclosure. The punch that I made for the first hole was not deep enough. I should have made a pilot hole to prevent what happens next. Not one of my finest moments, but mistakes will happen. I use these Knipex cutters for cutting spring wire when I make springs. This is also great at cutting small diameter screws. I'm soldering these connections instead of using quick connect terminals for the wire ends. The connection will be stronger and more reliable. I tin the leads on the connector, and I also tin the exposed ends of the wire so flux can flow between the surfaces and ensure a very secure bond with the solder. Once the wire end is melted against the already tinned connector, the solder makes a good and strong bond. I am making the connections that will be used for the shield of the cable. I intended to use number 8 rivet nuts. I didn't have the proper tool to rivet them in the hole that I created, but there is a way to use multiple nuts and a screw to do this, but the material of the rivet nuts did not allow this to happen, so I decided to use a better method. This thought process took me a while and a few trips to the hardware store before I had the idea to use 5/16 inch screws and modify them to be the connections I needed. This ended up being way better than I hoped. Tapping these holes for the 5/16 inch screw and with another nut on the opposite side of the enclosure wall allowed an excellent ground connection. This terminal strip will serve as the main connection for the torch height controller. The encoder connection on the controller will be used for the THC up, THC OK, and THC down connections. Pins 8, 12, and 13 are located on this connector. Pin 8 is used for THC up, pin 12 is used for THC OK, and pin 13 is used for THC down. On the ribbon cable, this is conductor 3 for pin 8, conductor 5 for pin 12, and conductor 7 for pin 13. In hindsight, it would have been better to use wire ferrules for these connections. The screw terminals are inset, making the openings more difficult to see. Wire ferrules would allow a more tactile approach in getting these inserted correctly. The connections I made here are solid as I tug on them, but wire ferrules may be more efficient. I'm connecting the THC as a dangling component so the customer can affix this to a DIN rail outside of the enclosure. This is important as the THC may need to be adjusted from time to time. Moreover, the THC uses a fiber optic cable to connect to another mating component, so this connection is easier to monitor from the outside of the enclosure. This terminal strip is used for the emergency stop, but there will be a few other terminals remaining for other uses, like limit switches. However, there are screw terminals for limit switches on the controller if the customer wishes to use those instead. This is a test of the motors and the THC. You will notice an E1 on the THC. This indicates that the fiber optic cable is not connected to the mating THC at the plasma, and no plasma voltage is being received. I'm using the test function on the THC to test the Z-axis THC up and THC down, and making sure the Z-axis motor spins accordingly. If you are using Mach 3, make sure to watch my Mach 3 plasma tutorial on how to configure the THC in Mach 3. If you are using Mach 4, make sure to watch my Mach 4 plasma THC configuration video. Go to my YouTube channel and search Mach 3 plasma or Mach 4 plasma. If you are watching this on the buildyourcnc.com website, these videos will be on the same web page as this video.